All right, so this is all about modeling, like real situations. They usually call it modeling, exponential growth and decay. So we could have problems about population growth, half-life, carbon-14 dating, different things like that. So there's a formula we're going to use every time. It goes A equals A sub 0, kind of like the initial amount. They put A0, that means initial amount, times E to the KT power. That's the formula we're going to be working with. So this A0, that's the initial amount. And then the A over there, is like an ending amount. Like when you're done, that's what the problem equals, obviously. So the A0 is the initial amount. And then the T is for time. I think most people know that. T for time. The K number, though. The K number is like a growth rate. If K is greater than 0, then the problem is dealing with exponential growth. And if K is less than 0, then the problem is about exponential decay. So if K is positive in the problem, then you're going to be dealing with exponential growth. If K is less than 0, negative, then you're dealing with exponential decay. And then E, that's just a key on the calculator. E is a number like pi. There's a key on the calculator for the E. You just have to find it. It's by the ln key. You usually have to hit second at natural log, and you'll find the E button. E is just a number like 2.718, like pi. So, yeah, and A at the end over here is just like your ending amount, what your problem equals when you're done. Okay, so they'll give you like some kind of scenario to look at, some kind of problem about population, or a problem about half-life. So let's just go through a couple of them. We'll just do like 2 problems so you kind of see how they work. Let's say that they tell you about the U.S. population. So let's say that back in 1970, for an example, in 1970, let's say the U.S. population was 203.3 million. Just a story problem the book gives to try to look at. So, yep, they say here's information. And then let's say by the year 2020, the population had grown to, and then they give you another number, 331 million. Find an exponential growth function that models this. Find an exponential growth function that models this. That kind of, so we're trying to figure out the function, like an equation like this up here. That'll help us to model that situation. Okay, so 1970, that was quite a while ago. It's saying the U.S. population was 203.3 million. Then by 2020, It's gone up to 331 million. Find an equation, a function. This is a function up here, some kind of equation you need. So what do you think? What do you think we should put for, maybe you could figure out some of these that I've labeled in red. What do you think we could put for the initial amount? Yeah, they're telling you, like, back a long time ago, the population was 203.3 million. So yeah, that's your initial amount, like we're starting there in this scenario. That's right, so that's like A sub 0 in the formula. Good job. Now think about maybe the time you could figure out next. The problem talked about 1970, which was a long time ago, and now they're going to compare to 2020. How much time has gone by there? Good job. So time is 50 years. Time equals 50, because just 1970 up to 2020, yep, that's 50 years. Good. All right, so let's start writing the formula. So we have A. Oh, what do we... Maybe we could figure out what A is. Because it's kind of like the end amount, like the ending amount. After the 50 years, what was the population? Yeah, I think we could put that for A. Good job. Because that's the amount at the end after the 50 years. Okay, so let's start plugging the numbers in. So 331, we could put that for the answer, because that was after the 20 years went, or the 50 years went by. Okay, A sub 0 was 203.3. E, you have to put E. Okay, we don't know what K is. They didn't say that in the problem. We know the time's 50 years. So that's how much we know, I believe. So we kind of have it set up, but we're going to have to find K from that. We're going to have to find K. All right, so this is 203.3 times E to the K times 50 power. Okay, so I'm trying to point out this is 203 times this E stuff. So if we're going to try to find K, we need to move some stuff around, try to get K alone. If you're trying to solve for a certain letter, you try to get that letter alone. So what do you think? Do you know what your first step is if we're trying to find this K answer? Yeah, divide by 203.3. Thank you. Okay, so let's take 331 divided by 203.3. So I got 1.628 equals, so now that 203 is gone, if you're dividing by 203, now it's E. We still have E, and we still have the 50 and the K up here. The 50, you can write 50K if you want, like 50 times K. All right, now some people know this and some others just need to learn how to do this. Now we want to get rid of this letter E. Well, how do you do that? Yeah, you take the natural log ln of both sides. So you have to get rid of this letter E that's there. So you write ln, that means natural log, on both sides. So you do natural log of 1.628 equals natural log of E to the 50K. Yep, so you take the natural log of both sides, that gets rid of, that's going to get rid of the E, because now we do the power rule, which we learned last class. See, this has this log, natural log to this 50K power. The 50K can go in front. It's the power rule where you can bring the power down in front. So I'll write that's called the power rule. For your logarithms, bring that in front. So now you have 50K times ln of E times natural log E. And over here you have natural log of 1.628 still. See, we're getting there. So power rule, you bring that in front. Now, what is ln of E? Yeah, if you didn't remember that, we'll write that on the side. ln of E equals 1. So the whole point of taking that ln of both sides is now this ln of E is going to go away. That's just a 1. That's just 1. So if you took 50k times 1, it's still 50k, right? Now you only have one more step, divide by 50, and then you'll get the answer. So then you'll take your calculator and take ln of 1.628 and then divide by 50, and you'll get the answer. So k equals, what do we get? Oh, let's round it off. The k, let's round it off to 2 decimal places. They'll tell you on your assignment, like round this one to this many decimal places, or... let's see. I think it's like a really small number on this one, I think. Just regular 50. Yeah, you take ln of that 1.628. Okay. So then let's round it to 2 decimal places. So what do you think? Yeah, 0.01. Because it's 0.0097. Yep. So they'll tell you on your assignment, round it this way. So see ln of that number and then divide by 50. So yeah, 0.01. That's k. All right, now the problem said to write a formula, find an exponential growth function. So let's write the final answer. They actually want the final equation. So the final equation is A equals, so the initial amount, the A0, was 203.3, 203.3 e to the 0.01. See, I can put the 0.01 now for the k times time. This is the formula then. This is the answer. You could then use that formula to find other answers, because they do have follow-up questions sometimes. First you go through and find k, and then they'll have a follow-up question. Okay, so then they'll say, oh, well then, how long does it take to have this population? You know, then they have more questions after. Like, what if I followed up with, okay, how long then till the population reaches 400 million? So they could have like a part B, you know, a second part to these, which they do a lot on your assignments. So then they might say, how long until the population reaches 400 million? What if they kept going? See, they do that sometimes on your assignments. I know you know that from doing these computer assignments, and there's always like another part. Oh, next step. So what if they then went on to say, how long until the population reaches 400 million? Well, then we would use this formula, and we would take the 400 million and put it in here, and try to figure out the time, how long it would take for that problem to get to 400 million. And it'd be kind of the same process again. We'd put the 400 there, and we'd put the 203.3 e to the 0.01 t. We would basically kind of do it the same way again. We would divide by 203.3. Once you kind of get going on them, they're all kind of the same problems. Even the second step. So then you take the 4. They'll usually tell you on the assignment, like some questions say round to 4 decimal places and some say round to 2. Each question might say different amounts to round. So let's see, 400 divided by 203.3 is about 1.97. Then you have e to the 0.01 times time. Then you take the natural log of both sides, and the natural log is just going to cancel out the e, because then you bring the power down and stuff like I showed you a minute ago. So natural log will just cancel out the ln e, like up here. So then you'll just have to divide. It'll just be 0.01 t equals this, and then you'll have to divide by 0.01. So once you get going, they're all kind of the same. The ln e will cancel out. It's just 1, and you can bring that power down in front, so it's just going to be 0.01 times time. So divide ln by 0.01. ln of 1.97, and then divide by 0.01. So this one I got it was ln of 1.97 divided by 0.01. That gives me my time. So I did it, and I got 67.8. And they might tell you to round it to the nearest year or something, so it could be like 68 years would be the answer. They might tell you to round it off to the nearest year. They'll tell you on each question like how to round it. They'll say, on this question, round to 2 decimal places. On this one, round to 4 decimal places. On this one, round to the nearest year. They'll tell you on each question how to round. So yeah, it's going to be like a 2-step process on most of them. First, you find the K, and then they'll ask you some kind of follow-up question. Okay, let's try one more. Okay, another one that, again, just another like situation they might do is questions about half-life, like carbon dating and half-life. Carbon-14 dating. You know, so they can tell how old something is when they find some like old ancient artifact. They do carbon dating and try to figure out. They can test and see how much carbon-14 is left in an object, and then they can figure out how old it is. So, again, we're going to use that same formula. A equals A0, A sub 0, e to the kt power. Same formula again. And then they'll give you some kind of story problem. So they'll say, this one says, it's from the book, it says, after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Will have decayed to half the original amount. Okay, so it says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find an exponential decay model. So find an exponential decay model. That means like find the equation. Find the exponential decay model. All right, so they're trying to tell you that it takes a long time for something to decay and decompose. So after this many years, it's like one of the key things there, the carbon-14 will have decayed to half the original. Well, did it tell us how much we originally had? No, so it's kind of weird. I know it's kind of weird. So the original amount, the A0, that's that original amount. They didn't tell you how much that is. You just have to know A0 is that original amount. they're telling you, like, at the end, after this much time, then your answer, like your A, is going to be half the original amount. So when we set this one up, it's kind of interesting. You're going to put this A0. They didn't tell you how much it was. You're just going to put that A0 there. They're trying to tell you after 5,000, so we know the time. We know the T in the problem is 5,715. This problem, this time they're trying to tell you it's going to equal half of whatever you started with. Half of the original. So you have to put 1/2 A sub 0 for A. Like for A, we're going to put 1/2 of the original amount. So it's kind of weird. So we you know, A0 is original. So the A in the problem this time, when they tell you about half-life, you can put 1/2 of the original over here for the A. So this one, I know it's kind of confusing at first. I always found this one when I learned it too. I was like, oh, this is weird. I have A0 and then just half A0. The problem just equals half of the original amount. So it's kind of different that you don't know the original amount and you don't know what half of the original amount is, but that's just how you set it up. You do end up doing the problem kind of the same way though. Then you divide by A0, divide by A0. So that A0 like is going to cancel out. It's just going to be 1/2. We're saying the problem's going to just equal 1/2. Kind of different. So we have this 5,715 years. Yeah, so if it just says half the original amount, the problem just equals half of A0. Kind of different. Then A0 is going to cancel out when you divide. Then you take that natural log of both sides. So then you take the ln of 1/2 equals ln natural log of e to the 5,715k. So see, every problem's kind of the same process. Divide, take the natural log of both sides, then this power can come down in front. Power rule. So then you have 5,715k times ln of e. Ln of e is just 1. We have to keep talking about that over and over. This ln of e, that's just 1. So this is still 5,715. Okay. Yep, this is 1. So that goes away. So this time you're going to type in your calculator ln of 1/2 and then do what? Yeah, divide by that 5,000 number. Yep. See, it's not too bad. They're all kind of the same. All right, so we could get ln of 1/2 is 0.5 and then divided by 5,715. Okay, this time let's round it to 2. Oh, this time, I don't know about your calculators, but mine says negative 1.21, and then it has this e, negative 4. Do your calculators do that sometimes? So I was using one of these big graphing calculators this time. Yeah, you do usually use one of the blue ones. But if your calculator it depends on what calculator you use. If it says e, that means like times 10 to the negative 4th power. So really that means this decimal should be moved back 4 places. So yours is right. It's giving you the right decimal. It's like let's see, I got to go back 4 places. 0.000121, something like that. Yeah, I used the graphing calculator so it was showing it with a exponent 10 to the negative 4th power. It just means move the decimal back 4 places. So there's your answer for K. It's okay if it's negative this time because this was talking about a problem exponential decay. Like something's old, it's decaying over time. So it's okay if you get a negative. Negative just means the problem was about exponential decay. So then we got our problem set up. So then we have A equals A0 e to the negative 0.000121 times time. That's just your formula then. That'd be the formula you'd keep using for the rest. So hopefully that helps. Like, we did a few of them, so you can see it just keeps going. Like, it's the same process every time, the same formula every time. So hopefully it won't be too bad as you work on it. Every time you have to divide by the A0 amount, then take the ln of both sides. Ln of e cancels out, so you just have that exponent, divide, and you'll get it. All right, so the problems are all similar like that. If you need help, I can come around and help you.